but I want to introduce Myles Allen from the University of Oxford, who heads up the Climate Dynamics Group. Matt England and I were asked by, I can't remember, Alejandro or David or Doug or someone to suggest a main speaker who would speak about climate change and some of the mathematical issues, and we decided to ask Myles, and he kindly agreed to do this. There was a question right from the beginning whether he would actually be able to come over here, and Alejandro said, yes, but this fits perfectly with climate change if he doesn't come, because we have saved all of the carbon footprint that would have been laid by his actually flying over here just to give this 1-hour lecture. So this has been very, very heavily practiced, so I think it will, hopefully will come off well. I should introduce myself first. I am Chris Jones from the University of North Carolina and University of Warwick. I am not this Chris Jones up here, who's a collaborator with Myles Allen, because Chris Jones, unfortunately, is quite a common name in England, as I have discovered through my life. Let me just say a word about Myles and why we wanted him to do this. He is one of the leaders in Britain and worldwide who is asking the really hard questions about predictions of climate change and what information there is in climate models and climate predictions. He set up and led the very influential initiative climateprediction.net, and if you want to have some fun someday, you should go on their website and look at it. It uses a group of people all over the world who are volunteers, and you can become a volunteer on climateprediction.net, where you run model examples on your own computer and give output to then the collective information which is used to assess, as I say, the information content in these climate model runs. So he was one of the experts included on the IPCC third assessment, and he also reviewed the fourth assessment report, although he might try to deny that now, I don't know. But anyway, I think it should be a very interesting lecture, and please bear with us if there are any technical glitches, but I introduce to you Myles Allen from Oxford, so thank you, Myles.
Good afternoon, everybody. Just before I get to that, first of all, I'd like to say thank you very much indeed for allowing me to participate in this way. I really wish it, as you say. I think it's a way in which we're going to have to get used to participating in conferences in the future, given the topic of my talk. I did actually to the ISI, I think it was. And it was really that trip which convinced me that I had to make more use of video conferencing, because I cycled to this talk, which is not something I'd normally be able to do, to give a talk in Sydney, unless I'm staying fit. So, just to check, one of the disadvantages of being remote is that you can't spot the body language of the chair. So what times are we specifically aiming for? I'm going to have to sort of do that myself.
Until about,
about 7 a.m.
Sorry, until, for about 50 minutes, if you could go until, right now it's 3:05 here. I can't remember what time it is there. 5
Yeah, that's fine, yeah.
It's 6:05.
Okay,
so
50 minutes should allow for questions. Okay, that's fine. I'd really like to have time for some discussion, because, I put some material into this talk which is new, and there's also some areas. I hope there'll be some debate with the people in the room over what I'm saying. So most of the focus of this talk will be on a recent paper with the title of the talk, which was published a few weeks ago, and my authors on that paper are acknowledged on the title slide. About the whole nature of climate prediction, because it's a new area in models. It's not a new area, but some of these issues are really coming to the fore, and issues hope your community would really engage in. So if we just go to the first slide, so hit return please. For those of you who aren't into this game of climate prediction, I thought I'd just put up a little reminder of where uncertainty in climate predictions come from. The first one, which for any of you who works on dynamical systems, chaos, weather forecasting and so forth, will be very familiar to you, is initial condition uncertainty. Basically uncertainty in what the system is doing now, where it's going right now. Technically, meaning by definition, this kind of uncertainty is irrelevant to a climate forecast. If you like, climate is defined as everything which has nothing to do with initial conditions when we're talking about the atmosphere-ocean system. So I could sort of ignore initial condition uncertainty by fiat, so to speak, but you should bear in mind there's always a little bit of ambiguity here because there isn't a clean separation between boundary conditions and initial conditions in the climate problem. For example, is the current trajectory of Greenland part of the initial conditions of the climate system or part of the boundary conditions? Okay, so you can see there's potential for a discussion that is not really the focus of what I'm addressing in this lecture, and I'm hoping that, I hope you'll bear with me that I'm talking about the factors that affect the changing moments of the weather and climate attractor, the weather attractor, which is the way we define the climate system, rather than worrying about the initial conditions which determine its trajectory over the next few years. Then the second source of uncertainty is uncertainty in how the boundary conditions of the climate will evolve over the coming century, for example. Now, there's two big factors here. There's natural driving of climate. The sun, for example, is currently apparently emerging, although it's dangerous to predict these things, apparently emerging from a solar minimum. So what's it going to do next? Is it going to recover to the levels of solar activity we saw in the 1980s, 1990s? Or, what's it going to do? That will affect the climate on a short time, but in a relatively small way compared to the other factors affecting climate. A much bigger factor is whether or not a large volcano will go off in the next few years. We have no idea when that will happen, and clearly that's an important source of uncertainty. But it's a bounded uncertainty in the sense that we do know the statistics of volcanic eruptions pretty well, so again that's a stochastic forcing on the system. And finally, there's anthropogenic forcing uncertainty. There's uncertainty in how greenhouse gas levels will evolve over the coming century. I'm going to explore a phrase from the Hitchhiker's Guide to the Galaxy, Douglas Adams. I'm going to call that somebody else's problem. So I'm just going to say, okay, yes, there is uncertainty in how greenhouse gas levels will evolve in the future, but that's something for the economists to worry about. And I'm going to assume that the problem I'm addressing is quantifying the response to a given profile of atmospheric concentrations or atmospheric emissions over the coming few centuries. And therefore, what I'm ending up focusing upon is what we call response uncertainty, or very often model error. And that's the subject of this lecture, meaning uncertainty in how the physical, chemical, biological climate system will respond to a given input of greenhouse gases. So if we go to the next slide, return, you'll see what I'm calling a recent failure of climate modelling. Now you may be surprised by that title, because this is probably one of the most famous figures to come out of the recent Intergovernmental Panel on Climate Change assessment. This is certified the summary of policymakers, and it shows on the left-hand side plumes of uncertainty for 4 different scenarios of future concentrations of greenhouse gases arising from different scenarios of future emissions over the coming century. And on the right-hand side, you see estimates of uncertainty in 2100 temperature from those different scenarios. Why am I then failure? Well, if you return 99% of the effort into this figure went into those plumes on the left, and those show you essentially the spread of results obtained from over 20 different climate models, supercomputer-based climate models run by the major modeling groups around the world. And so an enormous amount of computing, an enormous amount of scientific effort went into developing those plumes to give a range of model predictions for 21st century climate. Having done all that, we then, that is the authors of the IPCC fourth assessment, looked at the results and asked ourselves, does that actually give us a reasonable range of uncertainty? And came to the conclusion that it didn't, because the models were in effect too similar to each other for their spread to be used reliably as appropriate and accurate, a robust measure of uncertainty in future climate, in real world future climate. So the bars on the right, if you hit return once more, which actually had 99% of the impact of this figure, were obtained by a group of experts sitting around at a meeting saying, well, what do we think the uncertainty in 2100 climate actually is? And people argued about it and eventually converged on minus 30% plus 60% as a sort of likely, roughly one sigma range. So you can see immediately why I'm discomforted by this, because we've done all this work, we've run all these simulations, and yet in the end, the thing which really determined the headline results of the Intergovernmental Panel on Climate Change 2007 assessment, which was the point that the press picked up on and reported most heavily, which was the range going from slightly over 1 degree all the way up to 6.3 degrees, which is, if you just look at the bottom of the left-hand blue bar to the top of the right-hand black bar, that's what you get. That was the number reported, and that was based very heavily on this simple sort of exercise eliciting expert judgment at this meeting in Norway. It was, of course, informed by these model simulations, but the model simulation didn't really give us the answer we wanted, so we had to do a great deal of reinterpretation, and very subjective reinterpretation afterwards. So, the subject of this lecture is, how can we do better than that? How can we actually make the science of probabilistic climate forecasting more objective, more robust, and less dependent on expert judgment? So if you hit return, we should ask ourselves, step back a bit, and ask ourselves a very fundamental question: what is the aim of climate modelling? Hit return again. We had a conference in Reading last year, which concluded by calling, of course, you have a conference of scientists, they always end up asking for money, and it called for a revolution in climate modelling, which was going to cost a nice round $1 billion. Hit return again. One of the questions that I don't feel that conference addressed, and I still don't think has been adequately addressed by the climate modelling community. If you're going to have a revolution in climate modelling, how do you know when the revolution's over? What's your success criteria? Various ideas were put forward at that conference. Some people said we need a 25-kilometre resolution global climate model. Current models, well, the models used in those plumes on the preceding slide had a horizontal resolution in the hundreds of kilometres, maybe 200 to 300 kilometres. Everybody agrees that's too coarse to simulate the kind of weather we're interested in that causes the principal impacts of climate change. Whether 25-kilometre resolution is enough is very much open to debate. People who have 25-kilometre resolution models tend to say it's good enough. Those who don't tend to say we need much higher resolution. And some people are arguing for going down to 1-kilometre resolution so that you can start to resolve the actual clouds in the climate system. But of course, even at 1 kilometre, you can't actually resolve clouds which are much smaller than 1 kilometre. So, an even more radical requirement is that you should continue increasing your resolution until you don't need to parameterize clouds. For the non-specialists here, our parameterization is, when we talk about parameterization in climate modelling, I'm referring to the practice of representing sub-grid scale processes with equations relating the large-scale supergrid scale flow to the subgrid driving. So we can come back to in a nutshell, that's what I mean by parameterization. And it's the area in climate modelling where there's most judgment involved. The equations that govern the large-scale flow are essentially approximations to the Navier-Stokes equations. Those approximations are not entirely ambiguous. That the previous speaker was referring to some of the issues you have to worry about when you are making those approximations. But the real differences between climate models emerge from their different parameterizations of subgrid scale processes. And the final I threw in this as the final point for fun, but it was actually seriously suggested in a Nature editorial after this meeting in Reading that the real criteria of success was that people clearly aren't taking climate modelling seriously until we have bigger computers than the guys who build weapons. That's not really a success criteria, well, not one that I would recognise anyway. Okay, so if you haven't done again, I'm going to suggest an alternate success criteria. I hope we'll get back to talk about this at the end, which is that we should be aiming, in effect, to make climate modelling, or the specification of the individual climate model, irrelevant to the climate forecast. At the moment, we're in a very unsatisfactory situation where if you use the British model, you get one answer, if you use the American model, you get another one, and so forth. And for certain parts of the world, notably Australia, the prediction of Australian rainfall trends even the sign of Australian rainfall trends over the coming century is sensitive to which model you choose, and we don't know why. So, in that situation, it's a deeply unsatisfactory situation. I think climate modelling is failing Australia in that regard, in the sense that, what we can tell you at the moment is, the models say Australian rainfall might change, so you should prepare for that, but it's rather an unhelpful forecast if we're saying we don't know whether you should be preparing for more or less rainfall. And notably, this makes it very hard for us to say anything useful about the origins of the recent decade-long rainfall deficits in Australia. So, what I would argue should be a criteria of success in climate modelling is, no matter how you perturb your climate model, no matter how you vary the things which are uncertain in the climate model, notably the parameterizations, it doesn't make any difference to the distribution of future climates that you find are consistent with the quantities you can observe over the recent past. So, I'll unpack this whole concept in the course of the lecture. But let's go to the next slide. First of all, I'll start explaining one approach to addressing this, to producing distributions of future climates. There may well be many Bayesians in the audience, and I hope we'll perhaps have a bit of a discussion about this at the end, which I have been quite critical of, and I think has raised very serious issues in interpretation when it's used for climate forecasting. And this is the conventional Bayesian model averaging, it's often called, approach to setting up a probabilistic forecast. If I just take you through the terms in that top equation, I've used capital S to refer to any quantity predicted by the model. I've used S because one of the sort of quantities that climate modelers are very keen on predicting is the equilibrium response to doubling of carbon dioxide, often called the climate sensitivity. That's the equilibrium global mean warming when we double carbon dioxide and hold it at double pre-industrial levels indefinitely to find out what temperatures the system rises to. The reason this is a quantity that climate modelers are very interested in is that back in 1992, the world's governments agreed to aspire to stabilize atmospheric concentrations of greenhouse gases at a level which would avoid dangerous anthropogenic interference in the climate system. But they didn't specify what that level was, and so clearly, ever since then, the scientific community has been tasked to find out what the risks are associated with different levels of atmospheric concentrations of greenhouse gases, in order that politicians can decide what level they can punch for. And there's all sorts of arguments going on at the moment. Should we be aiming for 550 parts per million carbon dioxide? Would be roughly double pre-industrial. Should we be aiming for 450, which is not far above where greenhouse gas levels are at the moment, if you factor in the impact of other greenhouse gases as well as carbon dioxide, or should we be aiming for 350, which would require us reducing both carbon dioxide and other greenhouse gas loadings down considerably on what they are today. So S is just any quantity you might want your model to predict. Theta are the model parameters. These are these awkward parameters inside the sub-group scale representation of the model. Diffusivity is a familiar one to anybody involved in numerical modeling. But we have more obscure parameters as well. For example, one which we found to be particularly important in the model which we address is called the entrainment coefficient, which essentially dictates how much ambient air is mixed into a rising column of air in a tropical convective plume. There are no convective plumes in this model. The model grid is hundreds of kilometers, so much too big to actually resolve a convective plume, but we represent the physics going on in convective plumes in this model, and the entrainment coefficient is an example of one of these mixing parameters, which determines essentially the composition of air in detraining out of the top of cumulus towers in the tropics. Okay, so that's an example of a problem. So theta is a very high-dimensional vector, and I mean, normally theta would be dimension several thousand if you actually add up all the different parameters in a typical climate model, which would typically run to millions of lines of code. In fact, using a combination of the experience of the modelers and trial and error, we have found that it's possible to narrow theta down for typical climate prediction problems to a much more manageable size, in the sense that we tend to find, certainly in the model we looked at, and other groups have found similar results with other climate models, that the large-scale behavior is essentially driven by perhaps fewer than 10 key parameters in the model. And generally, the model developers know what those parameters are. They know, oh, don't touch that parameter, because if you touch it, you'll really change the forecast. In fact, we, for the first time, are the people who actually want to know what are those parameters are that they say don't touch, because we want to adjust them in order to find out just how robust the forecasts are. Y is vector of observations. That's quantities that the model stimulates that you can also go out and observe in the real world. And given that the model simulates these quantities and you can observe them, we can define a likelihood function, Py given theta, which is the likelihood of us obtaining the observations we do, given a particular set of parameters in the climate model. So that's a pretty well-defined quantity, the likelihood function Py given theta, and reasonably unambiguous, reasonably not dependent on the forecaster's opinions, so to speak. The real thorny one in this slide is P theta. This is the prior distribution you have to assign to the model parameters. And we'll address that in the next couple of slides. Finally, just as a point of PS given theta, just to explain this quantity, that's the probability distribution function for the forecast quantity given a particular set of parameters of the climate model. So you might think, well, this should be a delta function, because if I know my parameters, I'm going to know what the model's going to forecast. Well, typically in a climate model, it's a chaotic system, so you don't. You're only going to get a distribution you'll want to forecast. But in a simple model, such as the ones I'll be talking about in this talk, P estimate is a delta function. It's one of the parameters these give a particular value of the forecast quantity, 0 otherwise, and I'm going to be talking only about non-tonic single value forecast functions. But clearly it's possible to generalize this to multi-value problems. Okay, so if you hit return, here's an example, a very famous example of the first application of this Bayesian approach, certainly with general circulation models. And this was a paper by James Murphy and co-authors published in 2004. And the blue curve shows what they did to develop this figure was they ran a climate model, an atmosphere model coupled to a simplified ocean around 50 times, perturbing different parameters in the model. They then used something called an emulator, which was, many people in this room may well be using statistical emulators. This essentially is an interpolation scheme to predict what they would have got if they'd been able to run the model millions of times. So they sort of interpolated between the form to produce a synthetic, much larger ensemble. And the blue curve shows a smooth histogram of the results they got from that hypothetical million-member or so emulated ensemble for the climate sensitivity, that's the equilibrium warming when you double carbon dioxide. So the interpretation of that blue curve is, the way in which that blue curve is constructed is clear, but its interpretation, as I'll explain in the next slide, but hold it, don't go on yet, as I'll explain in a minute, is ambiguous. They then compared these models with observations and gave more weight to the models that matched observations better. And when you did that weighting, they obtained the red curve there, which shifted the distribution a little bit to the right, and gave their punchline answer. And the upper 5th percentile is highlighted there, of both the weighted and unweighted distributions for climate sensitivity, is around 5.5 degrees. Okay, so far so good. But crucially, in setting up this hypothetical million-member ensemble, the authors of this paper had to make some decisions about how to place models in model parameter space. Think of a parameter interval between 0 and 1. You've got to make a decision about how many models there are between value of parameter 0 and 1/2 versus how many there are between 1/2 and 1. Standard problem in Bayesian statistics. And unfortunately, in this particular class of forecasting problem, it matters a lot. Let's go to the next slide. If we just take the parameters they were sampling in that 50-member ensemble and adopt different, equally plausible sampling designs, you can have an enormous impact on the shape of the resulting distribution. The reason for this is essentially the shape of this distribution is being driven by the prior. The observations are not having a lot of influence here, and as a result, different priors give you very different posteriors. They give you a very different outcome. No Bayesian would be surprised by this. They just shrug their shoulders and say, well, that's just the way it is. Unfortunately, for climate modeling, and particularly for such a sort of controversial, politically pressurized problem like climate prediction, just shrugging your shoulders and saying, well, tough, that's just the way it is, isn't a very satisfactory response. So, in this particular case, for example, just by defining the entrainment coefficient, that coefficient I highlighted earlier, by its inverse in the model, so instead of talking about the ratio of ambient to convecting air, we talked about the ratio of convecting to ambient air, and then proceeding precisely as before, sampling the parameter exactly, sampling this new parameter exactly as Murphy et al. Sampled the entrainment coefficients in their original study, you can push out the upper bound of climate sensitivity from 5.5, which everybody accepts, reasonable upper bound, to something like 11, which alarms people. Possibility of double figure warming on 550 parts per million stabilization of CO2 would be extremely serious, because then we really are talking about a non-negligible possibility of runaway greenhouse conditions at potential levels of carbon dioxide that might well be achieved within the next couple of centuries. I'm not saying, incidentally, that the dashed line, that dashed red distribution here is correct, and if there's any journalists in the audience, please don't run away and start writing headlines on this. I'm just saying it might have come out of the analysis. There's no particular reason to favour the distribution published by Murphy et al. Over this distribution, and as a result, the Bayesian approach has some fundamental problems. Let's hit return now. And this is why I would argue that this conventional Bayesian approach won't ever work. I'm sure there's Bayesians in the audience, they may wish to come back to me at question time on this. The fundamental problem we have is that you have to sample, in order to drive this Bayesian analysis, you need to hypothetically sample a distribution of possible models. So you need to decide what your universe of possible models is, so that you can sample from it, and that requires you to define a distance between any two models in terms of their inputs, in terms of their parameters. And that requires you to answer the question, which I claim is unanswerable, about how many models there are between these two values of the parameter versus how many models there are between these two. And the answer to this question is arbitrary. And there's no way around that. And if your results are heavily contingent on how you answer that question, then it's very difficult for you to say anything useful to a politician. Well, worse still, it's possible for you to say anything the politician wants you to say. And that, of course, is a fundamental problem. And as long as the situation really arises because so many of these parameters don't really have a clear physical interpretation. There's no obvious reason to define the entrainment coefficients as the entrainment coefficient, or to define it in terms of its inverse. There's no obvious thing we can go out and observe the entrainment coefficients. If there were, then one could use Jeffreys kinds of arguments to argue for one sampling over another, and that actually would be a topic of another lecture, but I mean, maybe Jeffreys priors give you one route out of this. My experience, though, is that if you offer Bayesians the Jeffreys prior as a route out of this dilemma, they tend to tell you they don't like Jeffreys priors either, so the people who are trying to help don't like it, so maybe that's not a solution, but perhaps Jeffreys priors might be something we could come back to. Let's hit return. So this is my argument as to why we need a different approach, in particular when results are so heavily contingent on subjective choices made by the investigators. It's very difficult to avoid the impression that, at least, that investigators may be subject to external pressure to give the right answer. Perhaps, different countries tend to traditionally give a very different emphasis on the uncertainties in climate forecasting. And then it's very easy to get cynical and say, well, they're only saying they're confident in the climate forecast because they want a particular political outcome, or they're saying they're not confident in the climate forecast because they want a reverse political outcome, and so on. So we want to try and get away from this. So we need to come up with an alternative. If you hit return, we've argued that a much more robust approach is a much more old-fashioned one in terms of statistics, which is to look at, essentially, focus on the likelihood, focus on models fit observations without worrying about how many models there are in any particular region of parameter space. So I'm defining a likelihood function here, L1, as the maximum over all possible values of theta, possible values of the model parameter, of the product of Ps given theta, Py given theta. So Py given theta, you'll recall, is the likelihood of the observations for a given value of model parameters. Ps given theta is the likelihood of the forecast quantity having a particular value for the given set of model parameters. Ps given theta may be, it simply picks out the parameter values, or the subset of your universe of parameter values, that predict a given value of the forecast quantity you're interested in. And what we do is we maximize over theta, so we maximize over the model parameters to find what's called the likelihood profile. Essentially, it's the relative likelihood of the most likely attainable model as a function of the forecast. What you end up plotting is the relative likelihood of the most likely available model as a function of the forecast quantity you're interested in. What likelihood profiles do, I'll show you some in a minute, but think of, if you've just got a two-dimensional model, so two free parameters in your model, for every value of those parameters, so we've got a two-dimensional surface here in parameter space, every value of those parameters will have a goodness of fit to the observations to which I can assign the likelihood. And let me assume the high ones have a high likelihood, so I get this, probably, if the constraints are Gaussian, I'll get a Gaussian hump in my two-dimensional parameter space. Every value of those parameters also gives me a prediction of my forecast quantity. If it's a simple model, and these predictions are monotonic, so I can then take all these points and simply reproject them into forecast quantity, and then what the likelihood profile does is it just looks at the outline of that cloud of models to see what's the relative likelihood of the most likely available models as a function of that forecast quantity. Hopefully this will be clear when I show you some in a minute. But the crucial point about this is, provided you've sampled parameters densely enough to actually find what the likelihood profile is, it doesn't matter how many models there are in different regions of parameter space. So this problem of specifying a prior on model parameters doesn't arise. Let's go to the next slide. So here's an example of this in action. We generate many models. This is based on a simple model, but you can actually do this with more complex models, and this is actually what the climateprediction.net project is all about. But this is with a simple model. We generate many versions of a simple model by varying parameters within it, and we compare this simple model with two observable quantities. That's the 20th century temperature trends attributable to increase in greenhouse gases on the left, and the effective heat capacity of the atmosphere-ocean system. That's the amount by which the oceans, a measure of the effectiveness of the oceans in mopping up additional heat in the system on the right. And so you can see that these are two views, two projections of a three-dimensional, more or less Gaussian hump. So you can see, so those dots you're seeing there are points on the surface of a two-parameter multivariate Gaussian. Okay? Well, it's not exactly Gaussian, but it's a multivariate distribution. Okay? So it's clear what this plot means. However, each of these points corresponds to a particular settings of the model parameters. So we can take those model parameters and then run the model through at a time to predict something else, something we can't observe, like, for example, climate sensitivity. So if you hit return, the left-hand panel shows you the predicted climate sensitivities of each of those models. So each of the dots in the preceding slide corresponds to a dot here, and likelihood of that model, and the horizontal position of these points now is the sensitivity of that particular model. So you can, which as you can see, it's a rather different shape to the constraining distributions because, unfortunately, annoyingly, if you want to base your policies on climate sensitivity, it turns out to be relatively easy to generate, or easier at least, to generate models with a very high sensitivity that still fit observations, compared to generating models with a low sensitivity. So far, hopefully, reasonably unambiguous, and you can infer a confidence interval, not a probability interval, but a confidence interval from a plot of this nature by simply drawing a likelihood threshold upon it. The dotted line there shows the approximate sort of the 90th 5 to 95% range confidence interval. The likelihood that would correspond to a 5 to 95% confidence interval, and therefore you can take all levels that exceed that threshold as giving you a confidence interval on climate sensitivity, which is roughly 2 to 5 degrees. What this doesn't give you is a probability distribution function, and you need to be very careful here not to interpret that red curve, which is simply the outline around this distribution of points, as a PDF. And the reason for that is shown on the right-hand slide. Now, the right-hand side is another quantity you might want to predict with your climate model. This is the carbon dioxide concentration that gives 2 degrees of warming. Lots of governments are committed to avoiding 2 degrees of warming, so obviously a big question we keep getting asked is what carbon dioxide concentration should we aim for to avoid 2 degrees of warming. Now this is also something you can predict with this model. It's something we can't observe, but it's a forecast quantity that comes out of given settings of the model parameters. And there's a one-to-one correspondence between points on the right and points on the left in this figure, but there's a very non-linear relationship between the carbon dioxide giving a 2-degree warming and the climate sensitivity. That's more or less reciprocal relationship between them. As a result, if I take the red curve on the left and interpret it as a probability distribution function, and then just do an area preserving map of that curve onto the right-hand graph, I'll get the blue curve. And you sort of realize that the quantity plotted on the right is essentially 1 over x, if x is the quantity plotted on the left, and sort of go over that, then you'll realize that that has to happen. That it has to be shifted to the left relative to the likelihood profile for the red for the CO2 giving 2 degrees of warming. So this actually is what people normally do. They produce a distribution for climate sensitivity which probably looks something like what you're seeing on the left. And then they interpret that distribution to give them the risk of carbon dioxide levels needing to be lower than a certain level to avoid 2 degrees of warming. For example, it's this kind of argument that lies behind James Hansen's frequent pronouncements that we need to aim for 350 parts per million, because he looks at these distributions of climate sensitivity, sees that fat tail going out to high levels of warming, and concludes that we need to get carbon dioxide levels down to well below current concentrations in order to avoid those levels of warming. The difficulty here, of course, is that if you've never thought of climate sensitivity in the first place, if you've just asked yourself, okay, I've got my model, I've got my likelihoods, I want to predict the level of carbon dioxide giving 2 degrees of warming, you'd have plotted the points shown in the right-hand panel, you'd have plotted that red line around them. Why would you have ever thought about that blue curve at all? And that's the problem with the Bayesian approach. Let's go to the next slide. which actually just reiterates what I've just been saying. Sorry, I should have asked you to hit return earlier than that. But the key point is the non-linear relationship between climate sensitivity and the carbon dioxide concentration given 2 degrees warming gives you these problematic interpretation of anything you might describe as a probability distribution function for either quantity. If you want to use consistent posterior PDFs, you require a consistent prior, and that's going to be, one way or the other, it's going to be informative about one or other of these quantities. Let's hit return. So the problem we have with equilibrium climate sensitivity in particular is that it's not related linearly to anything we can actually observe. So all of these complicated philosophical questions become extremely problematic. And that was conventional policy of trying to specify stabilization targets, which appears to require a probability distribution function for climate sensitivity, is problematic. So is there an alternative way of approaching the long-term climate forecast problem, which is less sensitive to these issues? So in the last 10 minutes of this lecture, I'm going to propose an alternative, which we published quite recently. I've spent most of my time on the sort of philosophical preamble, because this is the area where I'm hoping, participants in PRIMA may have some thoughts, have some ideas, have some ideas about how we can resolve these issues. But now I'm going to move much more into standard presentation of results mode to tell you about this study we've done recently, looking at alternative ways of approaching the long-term climate forecasting problem without getting into the problem of specifying the climate sensitivity. These results were published relatively recently, if you want to follow up, and this is the rather cheesy cover of Nature on April 30th this year. And the question we're asking ourselves is basically what would it take to avoid dangerous levels of warming in the climate change problem. Just to summarize what we did, hit return please. You should now be on a slide saying summary of the study. I'm just forgetting to say hit return. Are we back in the sync? Yep. Okay, so you should be on a slide saying summary of the study at the top. Yep.
Yes, we're in sync.
Good. Sorry about that. So what we did was we generated idealized carbon dioxide emission scenarios by varying things that are different between different scenarios in the future. One thing which is different, of course, is the initial rate of exponential growth. We looked between 1% and 3% per year over the next decade. We then assumed there was some point in the future at which growth begins to slow down. We varied this between 2012, very optimistic date, and 2050. That type of the date at which emissions start to decline. This is the date at which the increase starts to level off. Then there's a rate at which the rate declines when you actually start to try and reduce emissions. So that's whether you turn it around fast or turn it around slowly. And then there's the maximum rate of decline that you think you can achieve, and we tried various rates up to minus 10% a year. It's worth mentioning that many economists and engineers think that minus 10% a year is completely unattainable with global energy systems, but we're just interested in what might happen if we were to do this, whether or not these scenarios are actually economically or politically achievable, is not the subject of this study. And then we simulated the response to these various scenarios using a simple climate model coupled now to the carbon cycle and constrained by observations. And we wanted to identify factors, we wanted to look at various factors that might be considered sort of summary determinants of damage, and particularly what I'm focused on here is the peak warming observed over pre-industrial, because this is really what's relevant to ecosystem damage and to many societal damage functions for the impact of climate change. So in return, this summarizes the recipe we use for generating these mitigation scenarios. So this shows the percent per year change in carbon dioxide emissions with assume either the rate of increase goes up and then starts to come down at some point in the future, and so on. And so we generate lots of different emission scenarios in this way. The meaning of the colours will become clear if you hit return, and we look at the emission scenarios that are generated by simply integrating out these rates of change. And the red and orange scenarios here are scenarios which have an integral, a cumulative emissions over the entire Anthropocene period, if you like, from 1750 to 2500, of 1 trillion tonnes of carbon, or that's equivalent to 3.7 trillion tonnes of carbon dioxide, or if you like, SI units, 1 hectogram of carbon. I'll come on to why we're interested in the integral in a minute, but let's just look at the response to these scenarios. If you hit return, if we just look at the response with the best fit values of the climate model parameters, you immediately see something very interesting politicians at least, which is that that large spread of emission scenarios, that large spread of orange emission scenarios on the left, gives you almost no spread in future CO2 concentrations. There is an orange band there in the middle panel, but you can barely see it because it's behind the red line. And there's an even smaller range of uncertainty in future CO2-induced warming. So what matters is the total amount of carbon you inject into the atmosphere. If you specify that, it really doesn't matter when you inject it, whether you inject more sooner and then less later on in the century, or if you start reductions straight away and then carry on emitting further into the future. This is quite an important point for the politicians to mull over as they decide what to do in Copenhagen. Let's go to the next slide. Hit return again. We're zooming in on those right-hand panels. This just shows you that the response, if we take the best fit values of the model parameters, you can barely see the range resulting from the different choice of emission scenario across the orange band, which all have the same total. Of course, the black lines show you very different totals and show you that you can get a very large range of responses, up to 4 degrees, and the ones I've just shown here, showing you a random sampling from our total, those have different cumulative totals. The ones that involve injecting 1 trillion tonnes of carbon into the atmosphere all give you much the same peak warming. Hit return, and of course, that was the best guess values for the model parameters. There is uncertainty in the response, shown here by the grey shading, which essentially represents the goodness of fit of these models to observations. And as you can see, the dark grey, the dark grey fuzzy band shows you where the most likely models predict the response to be. But there is a worrying tail of not particularly unlikely models going out to much higher levels of warming. If you hit return again, we can apply this to our full range of emission scenarios. I focused in those orange scenarios on ones which have exactly 1 trillion tonnes of carbon in total, but we can now explore over lots of different emission scenarios, and the grey shading here shows you the relative likelihood of different levels of peak CO2-induced warming as a function of the total amount of carbon you inject into the atmosphere. And the white crosses show you the best fit models. So the main point here is the white crosses all correspond to a fairly well-defined curve, and the coloured crosses show you taking a very different approach, fitting a different model to various modelling centres, resulting in the coloured lines also fall on the straight line. So it doesn't matter what scenario you choose, if you specify the total, you can predict the peak warming. If you hit return, this actually shows a slice through that figure at 1 trillion tonnes, and the curve, the orange curve, shows you the profile, the likelihood profile coming out of our analysis, fitted to models from more complex modeling centers. And the height of the dots shows you emissions in 2050 relative to 2010 in these various different scenarios. And you'll notice there's a big spread of dots in the vertical, very little spread for each individual colour of dots in the horizontal. And what's worrying, therefore, here is that emissions in 2050 don't actually determine peak warming. What matters is the total emissions. And what I find worrying is that the politicians who are arguing about emissions in 2050 rather than the emission total. So if you hit return, this raises the question, are all these lengthy debates going on in the run-up to Copenhagen actually talking about the wrong thing? Warming caused by carbon dioxide emissions depends on cumulative emissions, not on emissions in any given year. This is sort of highlighted by the left. This is a sort of summary slide, if you like, for the results of the study. On the left, you see 3 emission profiles with very different rates of peak reduction. The blue one goes up high, comes down fast. The green one starts going down right away and goes down slower. But they all give very similar temperature responses. So if you're arguing about how to achieve a particular level of climate change, the argument should really be about what's the total amount of carbon you plan to inject into the atmosphere, not the amount you plan to inject in any given year. Okay, so that's the key scientific result coming out of this. And if you hit return, we can just sort of put this into context. I'll wrap up in the next couple of minutes. To put this into context, let me show you how predicted warming as a function of cumulative emissions stack up against the amount of carbon currently sitting underground. So if you hit return, that's past emissions, which have basically already amount to around 500 billion tonnes of carbon. So it's taken us 250 years to release the first 500 billion tonnes of carbon. On current trends, we're predicted to release the next 500 billion tonnes in about 40 years. Okay? So if we compare this to what's actually underground, if you hit return, that's conventional oil and gas reserves would take us pretty much to the trillionth tonne, but not far beyond it. That's what's there in oil and gas. The big one is coal. If you hit return, that's conventional oil, gas, and coal. And if we include exotic forms of fossil carbon, such as tar sands and so forth, if you hit return again, you can see that that's more than enough carbon to take us well up into the sort of 5-6 degree warming territory where we really can't predict how the climate system will respond with current models. If you hit return, these are the conclusions, therefore, from this study. We conclude, cumulative carbon dioxide emissions over the entire Anthropocene period determine peak carbon dioxide-induced warming, and you can constrain that peak warming using past CO2 increase and observed CO2-induced warming. Crucially, you don't need to know the equilibrium climate sensitivity, which allows you to get out of these thorny issues of dealing with quantities that are non-linearly related to quantities we can observe. And the sort of somewhat explosive policy implication of this is the date and timing of the emission peak don't actually determine the risk of dangerous climate change. It's the total cumulative emissions into the atmosphere that matter, and it would be nice if this could be acknowledged by the politicians negotiating the next big deal on climate change to be concluded in Copenhagen. We hope to be concluded in Copenhagen later on this year. And the numbers at the bottom there just show that various other studies published around this time give very similar numbers for the total cumulative emissions, and also highlight the importance of cumulative emissions on peak warming. Anyway, I'd like to stop the questions now, so I think I've gone slightly over time, and thank you very much for your attention.